Yeah, so my topic is a Riemannian genuine measure of entanglement for pure states. So in this measure, in this talk, this is a joint work by myself and my supervisor, Radhika Vatsan. So in this talk, what I'll be doing is I'll introduce you some of the basics because to make it self-content. So I introduce to the audience what is entanglement and what's multipartite entanglement. And then the third and the fourth areas will be what we have defined in the work, which is bipartite Riemannian entanglement measure, and using that, how we defined a new measure for pure state entanglement, and which we called as GBR. And the last part is we compare the GBR with the other existing measures and show that how this measure has an advantage over some or many of the existing measures. And the last one will be the summary of all the contents. So I'm sure that many people in the audience might be introduced to this topic, but still, for an information theorist, what is entanglement? Entanglement of a bipartite pure quantum state is nothing but when you have a bipartite state and you cannot write that state as a tensor product or as a proper Kronecker product of two individual local states, then such a state is called entangled. To deal with it with a very simple 2-qubit example, consider the state this psi AB, which has been written here, which could be written as some coefficients associated with some kets. So I can very well write this psi AB as a tensor product of a local state A and another state B. So this is not an entangled state. This is a separable state. But if we look at the state in this box, this is a maximally entangled state. How much ever we try, we can never write this state psi AB as a tensor product as given here. So a state like this is called entangled. So any state which cannot be written as tensor product of two local states is called an entangled state. So, and these entangled states have very big implications in information theoretic protocols. So moving ahead, this is for two parties. So what happens when you have more than two parties? Let us first think of a very simple situation in which we have three parties. In that case, the separable states could be split into two kinds of separable states. One is a product states. Product states are the one which are split into three. Like if I have a state psi ABC, it splits into psi A tensor psi B tensor psi C. I can write that psi ABC as a tensor product like this. Then it's a product state. In the other sense, I can also have another kind of separable state in which one of the parties could be splitted, but the other two cannot. Like if you consider this state psi ABC, the 000 and 011 state, a 0 could be taken as common and that could be considered as A's qubit, like Alice's qubit. But the BC could not be separated. BC is an entangled state. So A could be separated from BC, but B and C are entangled and not separable. So considering biseparable states, we can have three different kinds of biseparable states in this system. Like I can have A disentangled from BC, similarly B from AC or C from AB. All these are biseparable states. So in the multipartite case, we have more types of separability itself. So now when we are going to define a measure, we have to take this also into consideration. So when we are going to define a measure, it's generally called genuine measure of entanglement. So if we have an entanglement monotone, and now we want to make it a genuine measure of entanglement for multipartite system, it has to satisfy two properties. One property is that it must be zero for all product and for all biseparable states. So any form of separability, our measure, if I put my state through this measure, my measure should say that this state has zero entanglement. And the vice versa should also be true, which means that it should be non-zero for all non-biseparable states. If I cannot separate the state, it should show a number which is other than zero. So these are the two main properties for a genuine measure of entanglement for any set of pure states. So now, once we know that we need these two properties into action, we can think of it as this way. Like if I somehow, I'm somehow able to find how much A is entangled with BC, like entanglement among one particular bipartition, if I'm somehow able to find, then I can multiply all these individual bipartitions entanglement and then find a geometric mean from them. And if you rethink the first properties P1 and P2, a measure that is defined in this sense will naturally satisfy P1 and P2. So even though if we have a very big multipartite system which has 10 parties or 20 parties, the question boils down to only finding bipartite entanglements. Like if I'm able to find entanglement among all the bipartitions, then the problem of an overall measure is solved. So instead of looking for something that obeys all these properties, I can always find a measure which is bipartite and then multiply them, find a geometric mean to define an entanglement measure. So that's the basic idea of this work. So this idea was already indicated by one paper which has been cited here by Peter J. Love. So which was I think around 2007 or 8. So using this idea, we take forward to define something called as a bipartite Riemannian entanglement measure. So it's based on a simple geometric idea. The idea is this: when we have consider we have a 3-qubit pure state space. So that space behaves like a hypersphere. So we have our state which looks like a smiley, for which we want to find how much entanglement we have. For this state, I want to find how much entanglement I have for this state. So one of the geometric approaches to find it is find all the closest biseparable states from this state, so which has been represented by hearts here. So if and then find distances from this, and which one is the closest, that much is the amount of entanglement. So basically, how far my state is from the closest biseparable state could be the amount of entanglement. So this is a very easy definition. Many authors write it, but the problem is that there is almost infinite number of biseparable states in this space. So it's like finding an infimum, a minimum among an infinite set. So in this space, in the 3-qubit space, this problem appears very hard. So the way out of this many number of iterations is that if we consider this bipartite, if we consider this 3-qubit state as in the reduced density operator picture, that is, if I want to find entanglement among A, B, C bipartition, I simply trace out A and look at the reduced density operator, which is BC. So in that goes into the block sphere or hypersphere of a 2-qubit system, where the state under consideration, the reduced density state under consideration, rho BC, lies in the interior of the sphere, because generally, if it's entangled, it will be in the interior of the sphere, and all the biseparable states naturally lie on the surface. So here what happens is, now in the previous picture, I was not able to find which is the closest separable state. But in this picture, since I know all the closest separable states are on the surface, all the separable states are on the surface, the closest one will be the radially outward one from this smiley. So from my reduced densities operator, which one is the radially outward state, that is the closest separable state, and that distance has the information about how much entanglement I have. So that's how we define a bipartite Riemannian entanglement measure, which is nothing but the Beur's distance between the reduced density operator rho AB and the radially outward point under for that particular rho AB, and with appropriate normalizing constant. So with this, we have a BREM, a bipartite Riemannian entanglement measure. So here we could have used any distance measure, but there is a particular reason why we went with the Riemannian metric or the Beur's metric. The reason is that it has a very natural curvature to it. So to indicate that, I have plotted that here. If you consider a single qubit space and you have a point in the center of the sphere and you try to measure if you keep moving the point from the center of the sphere towards the surface, even though the radius increases linearly, the geodesic distance from the center keeps getting curved as you increase the radius, and it goes to infinity at exactly 1. So because of this natural curvature in the Riemannian metric or in the state space itself, that gets handy for us in some of the advantages that this measure will pose, so which I will discuss later. So having this in mind, like I discussed in this slide in this equation, once I have a bipartite entanglement measure, I can always do this to get a genuine entanglement measure, genuine measure of entanglement, which is otherwise called as a GME, which is just multiply B1, B2, B3 and take the geometric mean of it. So for any generalized n-qubit system, I can always write which has m number of bipartitions. It's just this. So this is how GBR is defined, just product of all bipartite REMs and with an appropriate geometric mean. So yeah, the work is also in archive and it's under communication to journals. So you can always look at it for a more detailed derivation of what has been done. And now comes the advertising part, if you will. So that is, yes, as one of the questions is generally asked is, there are so many measures in literature, and why do you define one more? So here I have compared this GBR with the existing measures, existing genuine measure of entanglement. So the first one is GMC, which is genuinely multipartite concurrence, generalized geometric measure GGM, and the concurrence fill, and GBC. I've taken these four, which are most commonly used and highly cited GMEs, and we have compared the performance of our measure with these existing measures. So one suitable advantage that we find is this. So if you consider the states chi1 and chi2, if we look at it closely, what happens is like from chi1, if we do any local unitary operations, we cannot reach to a state that looks like chi2. And from chi2, we cannot go to a state chi1 by local unitary operations. In information theoretic sense, they are LU inequivalent states. They are two different classes in the state space. So in general, we expect any measure to parameterize the entanglement or to quantify the entanglement of those states uniquely, like entanglement of chi1 set of states and chi2 set of states, and need not, like, generally is expected to be different. But when you have measures like GMC or GGM, what happens is they consider the entanglement among only one particular bipartition at a given time. Because of that, though the plots of both chi1 and chi2, when we vary theta, appears to be the same. But in the case of our measure, and which is GBR and concurrence fill, we see a very nice differentiation between chi1 and chi2 when theta is varied smoothly. So this way of discriminance is achieved by GBR because it uses information from all the bipartitions, and concurrence fill also enjoys the same advantage because it uses the same set of information. And one more advantage that I would like to show to you people is, since entanglement is a physical quantity, when we are varying a state parameter theta smoothly, we expect the physical quantity to also vary smoothly unless or until there is an expected phase change or something happening there. But if you see GMC and GGM again in this plot, they show some sharp GMC and GGM, they show some sharp peaks in the plot which are not expected in general. So which GBR doesn't show. So why GBR doesn't show? That's because it uses the curved metric, the Riemannian metric, while these measures kind of use the information only from the Cartesian metric, the straight metrics like the trace distance, because of which they sometimes show sharp peaks when a parameter is varied smoothly. So this is a second advantage that GBR has over some of the existing famous measures. And concurrence fill is a recently found measure and it's been used widely. But the biggest disadvantage that concurrence fill has is it's based on a unique geometric representation, and its generalization to many qubits has not yet been given. And in general, there are papers which have shown that we cannot expect an extended version of concurrence fill for higher qubit systems. So even though concurrence fill is very good for 3 or 4 qubit systems, extending it would be mathematically very tasking or sometimes maybe impossible also. So in that case, GBR could be very easily defined for n qubit systems for m number of bipartitions. So to summarize all these results, I would say that GMC and GGM do not have a discriminance among LU inequivalent states, and they are not smooth enough. And of course, concurrence fill, even though has all these advantages, it could not be extended to many qubit systems, which is a major disadvantage. And of course, GBC and GBR stand equal, like it has all the advantages that is expected from a genuine measure of entanglement. But discussions on higher qubit systems might give us a meaningful comparison with GBC and GBR, which might be done in the future. So to summarize what I've talked so far, any n-qubit entanglement measure can be defined using entanglement among bipartitions, which was the first sum of slides. And then using this idea, we have defined a new GME based on the Riemannian structure of state space. This measure, GBR, is better than various existing measures for certain class of slates. The measure can be extended to mixed states using convex roof and other numerical techniques, of course. In the future plans, we intend to study the evolution of entanglement under dynamics, noise, and decoherence. Yes. So that's my